Bernoulli distribution, or even the Gaussian distribution. So here we define a link between y and z1 that is just a continuous latent variable, and then we obtain the MDGMM relating some mixed data to latent space that is very flexible, and it's just DGMM. Good. So now that we have the MDGMM, I will just skip the part about the training, and we assume that we have the model that is trained. It's trained from this port to this port, so you're learning all of these parameters. And then once the parameters are learned, such as a classical neural network, you can inverse the model just to generate from these learned parameters new observations that are discrete, non-continuous and continuous. Good. How do we do it? It's very simple. We use some simple Bayes rules. It is a model-based approach. Everything can be expressed as density of probability. So it's quite easy just to reverse the model from the trained parameters here with the tildes on it to generate some new observations here with some star. Going back now to applications and some results of the approach. We use the classical Azure dataset from the UCI repository that provides some census data on American individuals, such as the age, the gender, the familial status, or information about the income, about 30,000 individuals. And the idea is just to simulate some very rarely observed combinations of modalities of variables. For instance, combinations of age and gender, or gender and familial status that are not very observed. To do that, we have designed 4 experimental designs, which are actually just 2 designs that are crossed with each other and other combinations. So first, the bivariate design, here and here, that use which the goal is to generate some women that have more than 60 years old, that are not very observed in the training set. Here we have only 10 people in this training set presenting these observations, and to generate about 2,200 number of observations that present this observation, this crossing of modalities. We have also the trivariates. We are interested also in women of more than 60 years old, but that have a marital status that is just widowed. So very rare in the observations, and it could be very interesting just to reconstruct the parts of the statistical support that are not observed. So here we have 2 sub-designs that are just unbalanced and absent. So for each of the bivariate and trivariate, we let 10 people presenting the given modality in the training set for this design and design, and 0 people presenting this modality in the absent design. So the goal is to see if the algorithm can reproduce this type of people, even if it does not observe them in the training set here. So we are generating actually 10 training sets and 10 test sets, and each time in the test sets you have you have women of more than 60 years old and widowed women of more than 60 years old, and the goal is to have the same dependent structures concerning these individuals as in the test set. What are the benchmark models? The benchmark models, there are 4 benchmark models here. The CTGAN that are just based on generative adversarial neural networks for mixed data. You have SynPop that is based on cross regressions and regression trees, and you have Bayesian networks with data synthesizer, and data synthesizer has 2 versions, one based on CART and one based on random forest. We have used other benchmark models such as SMOTE-NC, that is a generalization of SMOTE for mixed data, and Edesine, but they presented very poor results, so we have decided for concision purposes just not to present them. 3 metrics, one to study separately continuous and non-continuous variables. For continuous variables, we are using the classical Kullback-Leibler divergence. For binary and categorical variables, we are using the mean absolute error. It's just comparing the proportions that are predicted according to our approach for a given variable and the one that are actually observed in the test set. And so we are just comparing these 2 quantities, making the sum of it. And then we wrap it up using a distance that is based on association metrics. The idea is that the more the dependent structure in the data set is well reproduced compared to the test set, the less this error will be. So we are having all of the data types computed and compared in this last metric. Presenting the latent space. Latent space here is a two-dimensional latent space, quite simple latent space. And what we see is that women and people of more than 60 years old are very well separated in the latent space, and that the new generated people data observations are interpolating between these two scatter plots. So we are in the good latent regions, and it's well identified. So it really is a chance that the data quality will be good. Then if I present you the MAE here, the green part is Miami, and the blue one is Citigan, the red one is SynPop, and SynPop card is the purple one. What we see is that Miami has very competitive performances on categorical variable. It's often outperformed by Citigan, but on continuous variable, it tends to win on Citigan. So we have a competitive approach when we are looking at the two data types separately. Looking at all the data types of the association matrix for all data, here we have a test set what we try to mimic, and here you have three competitors, Miami, Citigan, and SynPop. And what we observe is that the main patterns of the data set, so this pattern here, is well reproduced by Miami. It's not so well reproduced by Citigan, and is kind of good really reproduced by SynPop, but SynPop tends to put all dependencies in between all variables of the data sets. So if all variables share the same information, actually you're losing a lot of information. And Citigan, on the contrary, tend to be shy because it doesn't present all of the correlations. Some of them are just discarded or just diminished, whereas Miami tends to be more faithful to the original data set. Good. Now that I've presented you some stuff on the adult data sets, and which is more proof of concept than other things, I will present you a very rapid applications in microbiology, marine microbiology. The idea is just to assess what will be the future microbiology in the ocean when the temperature will rise by some estimations, say 2 or 3 degrees by maybe 50 years or so. So here we have 5 phytoplankton group, and we are simulating observations on which the temperature has rise. And the idea is just to see that they all benefit from it, except from this very particular group. They're all benefiting from the climate change and the rising temperature, which just show how adaptable they are to a changing environment, which is not to say that all organisms and from far will adapt so well to the different temperature change in the ocean. But this is maybe another debate. Good. So now finishing the presentations, what are the main future of axis of research and the limits of our approach? Here we have used an architecture choice of the MDGMM, that is the minimal architecture, to have very stable results. But it performs good in clustering, but we have not really tested if it's the best architecture to generate synthetic observations. So here we're using the modeling for another task, and we have not checked if this architecture was the most proper. The last point is about the way we sample in the latent space. As you have seen, the different regions are very, very well identified in the latent space, and we are sampling in all the latent space currently. So we could just identify the most promising latent space areas and sample in these areas in priority. This could be done using hyper-Bayesian optimization, for instance, just to very target the main interesting and to avoid rejecting a lot of observations that do not present the modalities that we're not interested in. Thank you for your attention. The package is available and will be available in final versions in a few weeks under the name MDGFM2 on GitHub. Thank you very much.
Thank you very much for your participation and the richness you have provided. If anyone would like to ask a question, we can handle them, please. Any question, please? Okay. Secondly, let's proceed with the study entitled A Galerkian Approach for Fractional Delay Differential Equations Using Hybrid Cheresko-Based Functions. Can we start?
Hello.
Hello.
Can I share my screen?
Please.
You can see my screen?
Yes.
Good morning, everyone. You hear me well? I can start?
Yeah, but your screen disappeared. Can you share again?
Oh, okay. It's okay?
No, we cannot see your screen.
Oh, sorry. Again. Now?
Now we can see.
Okay. Good morning, everyone. My name is Leila Moradi. I am PhD student from University of Salerno. My supervisor is Professor Diana Conte. This work is collaboration with these people you can see here, PhD student and other professors. My work is about Galerkin approach for fractional delay differential equation using hybrid Cheryshkov basis functions. This work divided to 5 parts. For the first part, I want to speak about problem and application. This problem, fractional delay differential equation, I divided to two kind of delay differential equation. You can see here delay is in the queue here and other delay here. Delay change between 0 and 1, and also you can see in this FDDE, fractional delay differential equation, you can see fractional of order alpha. This alpha change between r minus 1 and r. This kind of problem, fractional differential equation, they are application in biology, mechanics, electricity, and so on. And some authors interested to solve this kind of problem. I bring here some literatures about fractional delay differential equation that are recently worked. For the second part, I want to speak about some introduction we need to them in this work. For this work, we need to speak about fractional integral of order alpha and also fractional derivative of order alpha. Here, I bring Riemann definition of Riemann-Liouville fractional integral of order alpha and also Kapitov fractional derivative of order alpha. You can see in this slide, and I can say that alpha change between n minus 1 and n. For solving our problem, we want to use hybrid Cheryshkov polynomial. But for the hybrid Cheryshkov polynomial, we should introduce Cheryshkov polynomial. What is Cheryshkov polynomial? These kind of polynomial are continuous. They have weight function equal to 1, and they are orthogonal on interval 0 and 1. And this is the orthogonal condition of this kind of polynomial. And here delta is delta Kronecker. And this is definition of Cheryshkov polynomial. Sorry, you hear me?
Yes.
Okay. Okay, I continue. For hybrid Cheryshkov polynomial, we use Cheryshkov polynomial and also black pulse function to define a hybrid Cheryshkov polynomial here. This kind of polynomial also they are orthogonal, they are continuous, and the degree of this kind of polynomial is n. Here, phi and m are bases of a hybrid Cheryshkov polynomial, n equal to 1 to m, and also m equal to 0 to n. Every function can be expanded by a hybrid Cheryshkov polynomial we introduced here. Here, you can see in this expression, this FT expanded by phi t hybrid Cheryshkov function and also CT. CT is unknown that we should determine them to for solving our problem. And here phi t is consists of a hybrid Cheryshkov polynomial. Okay, for solving our problem, we need to speak about one theorem. This theorem is about Riemann-Liouville fractional integral of order alpha. When we have phi t as this phi t as a vector consists of hybrid Cheryshev polynomial, we can expand them by using of hybrid Cheryshev polynomial, and also we have here matrix. This matrix is fractional integral matrix of order alpha, that every element of this matrix is same as this element. Okay, for numerical method, in our method, we have a fractional derivative of qt. So we have this function. We can approximate this derivative, this fractional derivative, by using of hybrid Cheryshev polynomial and also unknown coefficient c. When we determine c, this coefficient c, we can have our qt. So we expand by using of fractional derivative of qt by using of hybrid Cheryshev polynomial, and then by using of a fractional integral in each side of this equation, this expression, we can extract qt, and then in our problem we have a delay of tau for the product and also for the minus. So we use t minus t in this expression and have this equation, and also for product. And then by using of residual function RT for each problem, for product and minus, we can and also by using of roots of shifted Chebyshev polynomial, we can put all of them equal to 0 and determine c, coefficient c, and then when we put c here, we can have qt and our problem solved. Demonstrate to this our method working good. I bring here three examples. Here in first example, in the graph you can see in the left picture of this figure, you can see when alpha convergent to 1, here alpha between 0 and 1, and when alpha convergent to 1, here the graph, our graph, all of graph close to graph when alpha equal to 1, and the right picture says that absolute error of this example shows that this method works good. And this absolute error is for when alpha equal to 1. This table shows the comparison of our result with other reported result for root mean square error, and you can see our result. They have agreement with some of them and better than others. For the example 2, again we have these two figures. Left picture says that when alpha between 2 and 3, and when alpha convergent to 3, here alpha convergent to 3, the approximate solutions close to when alpha equal to 3, and this figure shows absolute error when alpha equal 3, and this is power to minus 9, shows that our result works good. And this table shows again some comparison with other reported result. This result, our result, they have a good agreement with other reported result in different value of t. For the example 3, again, we have this example, this kind of example with the product delay. And again, left picture shows approximate solution for various values of alpha. They are close to approximate solution for alpha when alpha convergent to 2. They close to alpha this graph when alpha equal to 2, and they are absolute error. This figure shows absolute error, and this power -10 shows that this method works good. And this table, last table, shows comparison between our result and another reported result in reference to I bring later, and they are better than this result, better than other reported result, and for different values of t. These references are the authors worked recently about the fractional delay differential equation. And thank you for your attention. If you have a question, I am here to.
Thank you for your contribution with your successful and your presentation.
You're welcome.
Thank you.
You're welcome.
Could I get the question, please?
Yes.
If anyone would like to ask questions, we can handle them, please.
No questions from inside.
No question. Okay, all right. In the third sequence, the study name, a table research with a double neighborhood strategy with authors Paula, Anna, and Miguel. Can we start, please? Okay.
I should sit here so I can be Okay. Hey, good morning. Thank you, my friends, for being here. It's a pleasure. Okay, so it's a real pleasure. Congratulations to the organizers. Everything is going very smooth and very well. So, okay. So this is a work that started from a real application. So we had a work with Galp, and they asked us to develop a vehicle routing problem. And from this work, this idea has appeared, and we explore it beyond the scope of the solution in Galp of the vehicle routing problem. So I just want to give you a motivation for this problem, give some concepts about taboo search. I imagine that everybody here knows about taboo search, but still just to mention a few issues. Then to introduce the idea of using a double neighborhood and the application to a knapsack problem and reporting the computational experience. And in the end, I just going to give some short insights about the vehicle routing problem that we are solving and the results that we obtained. So this vehicle routing problem is a very complex problem, and if I have to give in detail all the applications, all the issues about the application of taboo search, I will lose too much time. So I have preferred to give you the applications for the knapsack and then show also what happened for the vehicle routing problem. So we know that taboo search is a very good method to tackle the hard optimization problems. In part because we don't need to have a mathematical formulation of the problem to apply taboo search. We just need to encode the solution in a good way, and then it has showed many good results for these problems, in particular for instance, scheduling problems, timetabling problems, vehicle routing problems. So there were a very good results for the application of taboo search. So of course it is an heuristic. So the drawback is that we don't have in general the idea how far we are from the optimal solution, unless we do something different to get lower bounds. Otherwise we don't have the idea of this gap. But this is what we should apply when exact methods are too costly. And I had another student doing application of a vehicle routing problem for the posts in Lisbon, and we try an exact method, and in fact we transform it in a heuristic later because to apply Cplex to this formulation was too costly, and we didn't have solutions in a short time. Of course, there are other drawbacks that the strategies must be refined, because what works better for an instance does not necessarily work for another different instances. And the problem is, especially when you have many local optima, then the taboo search has some difficulties in escaping the zone of attraction of local optima. And this, of course, can slow down the process, and it will only work well if you are able to look for many solutions. So to explore as widely as possible the solution space. And then if you take too much time to escape from local optima, you are going to compromise this goal. And of course, if the strategy is to evaluate the neighborhood solutions, then this is again the problem, that you have less time to explore new solutions. Okay, so the general idea of a taboo search is something like that. You start here with a point, you look for the best solution in a neighborhood. What is a neighborhood of a solution? Are solutions that are close in some sense from the center of the neighborhood, in the sense that you have a rule that defines how to transform this solution in the middle from other feasible solutions in the neighborhood. And then you choose the best solution, and for that you generate again the neighborhood, and then you find the best one and you continue, okay? And then if you arrive to a local minima, then you have sometimes difficulties in escaping these local minima, because there is a strategy in taboo search, which is the taboo list. And taboo lists are rules that avoid to go back to the previous solutions. And this sometimes is not enough to produce a good escape of this area of attraction of the taboo search. So a taboo search, very basic one, starts with the initial solution, okay? And you always keep the best solution found so far, which is this X star. And then from this solution S, you generate the neighborhood solution. You find the best solution. So if you are minimizing, is the one with minimal value of the objective function. If you are maximizing, with the highest value of the objective function, that is not taboo, means that is not forbidden. Then if it's better than your incumbent solution, you just update it. And then the best solution found is the center of the new neighborhood in the next iteration, and you update the taboo list. So this is the general idea. There are many features regarding the taboo search that can deeply influence the result, the outcome. The first is the initial solution, that it sets where you are starting to search, how you search this search space, what is the structure of the neighborhood, because what is to define what is in the vicinity of some solution can be done in very different ways. You can have very simple neighborhoods where you just change your variable, or you can change a set of variables, or you can have more complex definitions of the neighborhood. Then you have the taboo list. The taboo list, the ideal should be to keep the solutions that you have visited to avoid going back to a previous solution, but then this will be a huge list and difficult to manage in memory. And so you just usually use a move that you cannot do, and this move is the kind of move that not only will take you to the previous solution but also blocks other solutions. This is why this is important to have it just for a few periods, which is the taboo tenor measures how long you are going to keep this taboo on your list. Then you have many other features like the aspiration criteria, which allow you to revoke a taboo status. What is your stopping criteria? Do you want to find a good solution of a value above something? You want to do these iterations, this time that is going to define why you stop. Then you have strategies of intensification and diversification. Intensification means that you are going to look deeper into some region. Diversification meaning that you want to move to a different far region to explore the search space. Then you have multi-start. When you get stuck in the taboo, you may restart from another point that you generated. So as you see, you have here many things, and you must do an engineering of these features and see what gets the best results for your problem. So the motivation for the double neighborhood is the following. So imagine that you start here with x0, okay, and you define this neighborhood, and in the neighborhood the best point is x1, so it defines the center of the new neighborhood, which is this one, and in this neighborhood the best point is x2, and you are here, okay, and this is a local minima. So now to escape from this local minima, if you continue with the strategy of looking for the best solution, okay, you will leave this region very slowly, okay, because you are always choosing the minimum. So instead of escaping the zone as quickly as possible, you are going to continue here on the best point that it's not x1, would be a different one, and then from this one the minimum will be this one, and so on. So you will take many iterations to escape a local optima. So our idea, looking at the data that we have from GALP, the idea, you saw that this local minima produced a very deep valley, okay, because if it's a spread valley, then you can easily go out, but it's very deep. Then it took a lot of time. You are always finding the center of the solutions are always worse than what you have in several iterations. So the idea we had is, if you want to escape, why don't we, once we find that we are in a local optima, and you get a certificate that is a local optima, because in several, let's say 3, 10 iterations, you always get solutions worse than your center. Why don't we leave this region by trying to maximize instead of minimizing, okay? So this idea started developing, and we thought, okay, we have very different ways of exploring this. We can have just one list, one line, and then when we see that we are stuck in a local minima, instead of using minimization, we switch to maximization. But then we may lose solutions because we may go over some good solution that it's also a local minima. So the idea was, say, let's keep two lists separated, okay? One is doing minimization, the other is doing maximization. So, and we switch, okay? So when we see that we are on a local minima, we switch for this list from minimization to maximization. And we have a list that does maximization, that in a way is also taking us away from the search that we are doing with the minimization. And when we get a local maxima, we switch to minimization to try to find a local minima. And so this is the game that we played here, okay? So the proposal was a double neighborhood strategy with opposite optimization directions, using minimization and maximization independently of your problem being minimization, maximization. And then you have two parallel processes running at the same time, and you switch from minimization to maximization, where in consecutive iterations there is no improvement, and you see that you need to escape this attraction zone of a local optima, either it's a minimization or maximization. So we apply this to a vehicle routing problem, a real problem with very good results, but I'm going to show you just application to a knapsack problem, because knapsack problems are really easy to describe, and there's also many important applications. So the idea of this change of neighborhood, you start in the neighborhood, if it is maximizing, if you reach a local maximum, you change the strategy to minimization. For the list that it's minimizing, if it takes a local minima, you switch to maximization, okay? And the reason why to choose the knapsack problem is because it has many interesting applications. It's very simple to describe, and it has applications, for instance, in optimizing investments, cargo loading, capital budgeting, as an example.
Сами себя. Я боюсь, что не все 4 доклада месяца сделал. Сам Германия.
Mic, please.
Maybe you can mute them, right? So it is this guy and okay, thank you. Okay, so the formulation is well known. You have variables that are x, y, taking value 1 or 0. Just imagine that you have a knapsack and you want to put there inside objects, and you want to choose a subset of objects that will maximize some value function, and you cannot surpass the capacity of your knapsack, which is P, and every object is a certain weight. For instance, in investments, X P is the value, the cost of this investment. Capital P is the amount that you have to invest, and V is the expected return of this investment. So as an example of an application, okay? So we use data set from this repository to test our problem. And so to apply the Taboo search to this knapsack problem, you just encode your solution in an array of zeros and one. We use a very simple strategy, just changing 1 0 to 1 or 1 1 to 0 if feasible. To fine-tune the taboo tenor, you try different values for the taboo, and the taboo was just this move. Okay, so if in one solution I have the 0 in position 6, that changes to 1. I did not allow in position 6 or 1 to become 0 again. So this was our taboo. And in the second neighborhood, there is an extra parameter that is how long you wait until you switch from min to max. So if you have a iteration where you are not improving, how long that you have to wait, okay, to do this switching. So this is the number of elements of your knapsack, from 10, 7, very small problems, to 2000. And this is the known optimal value. And we can see that this first column is the best solution obtained using just one neighborhood. This is obtaining 2 neighborhoods. And this is the iteration that, this is the value from the neighborhood 1. And this is the value that you obtain by the neighborhood 2 in the same process. And this is the iteration where we obtain the solution. So, of course, we see here that we were able to get better results by using this double neighborhood. So this graphical presentation is probably better to see. So just remember that you are maximizing, okay? So the orange line represents the values obtained using the neighborhood 2. The blue line is when we use just one neighborhood. And here on the x-axis, you have the different taboo tenor. Taboo tenor is the number of iterations where a taboo remains in the taboo list, okay? And remember, this is a maximization problem. And in fact, we got better results, okay, for the same taboo tenor for the using the strategy of 2 neighborhoods in general, okay? So to just add this presentation, just some insights on the vehicle routing problem that we are trying to solve. It was a very complex problem because from the usual constraints that we had, that the route starts at Saint-Depont, this is normal, but we also had the constraint that the route could not exceed 9 hours per day. We had different vehicles with different compartments, and in each compartment we could have different products, okay? So this made the problem more complex because a car has in general 2 or 3 compartments, and they can be filled with different types of products. Of course, the maximum load weight cannot be exceeded. This was okay, but we had also a different feature that we have priority customers. So the Galp serves hospitals and the airport and the pump, the fireworks, and this is a contract, so they can go there and replace the petrol by in 1 week. So you have, let's say, 1 week, and in 1 week you have to go there, but you don't need to go on the next day. You have 1 week, and you had priority customers, which are the pumps in the cities, okay, that don't have a big capacity. And so when they put order, you have to deliver on the next day, okay? So each customer must be visited only once a day by a single vehicle, unless exceptional cases. And we had exceptional cases, for instance, because the hospitals needed more than just one vehicle. So we had to be visited more than 1 day to fulfill the order. And there was time windows in this problem. And it also happened that the vehicles that we had could not go to every client. So for instance, in the city, only the small cars were allowed. So we had also this constraint of the type of car or vehicle that could visit a client in certain areas. So just to end my presentation, so you see we had the data for several days. We tried 13 days, data for 13 days. This is the total distance that it was done. And the iteration where we got the best solution using neighborhood 1 or neighborhood 2. And you see here, not always, but in many situations, we had best results when you use 2 neighborhoods instead of just 1, okay? So this was a master student that now this work is going to continue with a second master student in Galp, because the problem is too complex. Anna was able to deliver a solution, to deliver a program that did that, and she did a fantastic work. But there are other things to continue, and we have another student continuing her here in Galp. So this is our proposal, to use taboo search with 2 strategies where we switch from minimization to minimization in the search. So thank you so much. So I don't know if you have questions.
Thank you for your contributions with your successful and your presentation. If anyone would like to ask a question, we can handle them, please.
Yeah, maybe I have a question.
Yes.
concerning benchmark model for the approach on the very particular last VRP problem. Have you
Sorry,
compared?
can you speak slower? The sound is not perfect. So if you can speak just a bit slower, I can understand your question. Yes, please.
Good. I had a question about the last slides that you just presented us concerning
Yes.
the VRP model, the VRP problem. Have you tried to benchmark your model with already existing operational research or graph theory based model?
So you mean with other models or other benchmark data sets?
No, on these data sets and this problem, have you tried other benchmark models?
Well, no. As I was trying to explain, this was a master student. She had something like 3 months to deliver, 4 months to deliver results. So we were very focused on giving an answer to the company. And as I said, and thank you for the suggestion. Yes, we really want to continue exploring this idea, and of course to search for other models and other instances, other benchmarks. It's surely one of the things we will do in the future. Thank you so much.
Okay, thank you very much.
Any questions?
Yes, we have one in the room. No, you can say it, and then I will say.
Your strategy is very clever, and you try to find not only device. My question is, it's a smart strategy to explore center, but when you are climbing, somehow you are overlapping the path of going down. Is it possible in a strategy to save some computational time to start somewhere in the beginning of going down using the minimizer?
Yeah, that's what I said. I mean, you can use this software just like the replace, okay? So the question was about how to use this strategy in a different way, trying not to overcome a possible minima that may exist in the maximization process, right? Okay. Yeah, there are. I mean, we can explore this idea in so many different ways. Okay? As I told you, we were constrained with time because then I had to deliver it. But yes, we have been thinking about different ways to explore this. But what you are mentioned can even happen in the normal taboo search. Okay, that you just surpass a good minimum, because it all depends on the taboo tenor, on the taboo list, on type of neighborhood. So this is why you have to do after that an engineering process, because even in the normal taboo search, it's possible that you escape a minima in this process because you didn't get it on the neighborhood. So the neighborhood is not truly a physical neighborhood where you are going to see all the solutions that are there. Okay, so you pick points from the neighborhood depending on the way you define the neighborhood, but between these, with a different definition of neighborhood, you could obtain a better solution. So this is, taboo search is very nice and very interesting, but it has all this engineering that you need to explore in the end. Okay, for instance, I had a previous work on taboo search with exams timetabling, and we were developing an automatic system to define the taboo tenor. We had a decision problem, okay, and we did that in an automatic way by looking at the historical data of our search and defining, depending on this, with using a multi-criteria problem, deciding how long this taboo will stay in the taboo tenor. So, in fact, there are so many things that can be done, and thank you for your question, your comments. Okay. So I think that's done.
We would like to thank you all the participants for their contributions, their time, for the presentation, and for their dedicated work. Um, Thank you. Hoping
Okay,
to
thank you.
meet you again next year by bringing together novel and high quality studies. Thank you very much.
Thank you. Thank you.
Thank you. Bye bye.
Thank you.
3:30 Е. Что, в 10:50 не будет, что ли? Ладно.
Бегать наверх, пока не поздно.
Пять минут осталось. Тут никого нет. Вернее, есть.
Hello.
Hello.
So you are the first two presenters, right?
Yes, I will present first two presentations.
Perfect.
Excuse me, may I try to share the screen?
Just a second. Yes, please try now.
So do you see it now?
Yes, perfect. We can. I
Okay.
can see the screen.
Okay, okay. Should I close it?
Yeah, like for now, maybe yes. Like I'm waiting for
Okay.
the chair
Okay,
start.
okay.
Is the third presenter here in the online?
Vadim Lisitsa. So, good morning. We are starting session 9B. The title is General Track 1. Thank you, Jitsam, for the support. The first presenter is Kirill Gadishin and Maxim Protasov. The presenter is Maxim Protasov. The title of the paper is Full Waveform Inversion of the Scattered Component of the Wave Field Resolution Analysis. Please.
Thank you, Mr. Chairman. Do you hear me?
Yeah.
Do you see my screen?
Yes.
Yes.
Okay. So my name is Maxim Protasov. Kirill Gadilshin was supposed to present, but he cannot do it. So this is title of the talk is Full Waveform Inversion of the Scattered Component of the Wave Field Resolution Analysis. And this is joint work with Kirill Gadilshin. So content of my talk is the following. So first I will present briefly the motivation, then I will show standard full waveform inversion results, FWI results. Next I will come to diffraction FWI results and show singular value decomposition analysis of the diffraction FWI operator. And I will finalize with the conclusions. So the motivation. So
excuse me, are you sure you're sharing the correct window? Because we are seeing only the
beginning page.
The base presentation with the list of...
this is fourth slide now. No, you don't see it?
No. We see another window. So please, if you can share again. If you share the entire screen, probably is the better solution.
Okay.
Now it's okay. Now it's okay.
Now
it's okay.
Fourth slide, yes.
Okay. Let me do like this then.
Yep.
Okay. So the motivation. So it is well known that scattered waves provide higher spatial resolution and they are widely used for diffraction imaging. And FWI is a procedure for constructing high resolution depth velocity models, and usually it uses diving and reflected waves mainly. However, the influence of scattered component of the wave field in the inversion process has been poorly studied, and therefore, but theoretically, the resolution of the method when using scattered waves should be higher. So thus, in this work, we aim to assess the influence of the scattered component of the full waveform inversion on the quality of the inverse problem. Now I come to the full waveform inversion, standard full waveform inversion experiment. So we assume the wave process under study is described by the scalar Helmholtz equation for a two-dimensional inhomogeneous medium. It is convenient to use as a model M, the squared slowness, and by operator F of the forward problem, we mean a mapping that assigns a function M, the model, to a solution of Helmholtz equation for the number of sources and receivers. In this notation, the inverse dynamical problem of constructing a velocity model from seismic data is reduced to solving a nonlinear operator equation like this. And the general FWI formulation is to find the minimum point of the misfit functional, characterizing the mean square deviation of the recorded data from those calculated for the current velocity model. So we carry out all consideration using the synthetic velocity model shown in this figure. This is modified Marmouzi P-wave velocity model. The first experiment aims to investigate the contribution of diffraction to the reconstruction of depth velocity model by standard FWI. For this purpose, a wave field separation procedure is required to extract the scattered component, and we provide FWI without considering point deep diffractors, and then we will focus on the contribution of these point deep diffractors located approximately at depths 3,100 meters. So for this purpose, we calculate the observed data for the Marmouzi model without diffractions, this data, and with diffraction, this data. And we take the difference, and thus we get the wave field that generated by diffractions only. And for the inversion, we use a highly smoothed true model as the initial model for the inversion. And the result of the standard FWI inversion procedure after 235 iteration of nonlinear conjugate gradient method is shown in the middle. And the inversion was carried out in the frequency domain for 11 time frequencies from 5 to 15 Hertz. And as one can see, the reconstructed model is rather close to the true velocity distributions. And now, this is first experiment, and in the second experiment, attempts to refine the obtained model by adding deep point diffractors to the inverse problem. We use the observed data where we have diffractions only, and we use the model after standard FWI as the starting one, and run the same FWI procedure. As one can see, adding depth diffractors to the inversion process does not significantly change the inversion result. However, the model update contains predominantly high spatial frequency, which may be because of the theoretically high spatial resolution of diffraction events. Now we come to the FWI using diffractions only, and we introduce the following notation where model M star is the Marmouzi model after addition the depth point diffractors. M0 is the starting model for the inversion. DM1 is the desired velocity perturbation we wish to recover using full waveform inversion, and DMD, this is a depth point diffractors, models that correspond to depth point diffractors. Consider the original statement of the inverse dynamic seismic problem, and using the notation introduced above, we provide the linearization of the problem. And based on the expression we got, there is a clear connection between the model perturbation and the corresponding perturbation in the data. The scattered component of the wave field associated with the presence of depth point diffractors is a very small order of magnitude, and this explains such behavior of the FWI procedure in the standard formulation that we already shown in the previous experiments. But how can this be bypassed? We see two options. The first option is similar to the previous FWI experiment, except that all considerations are carried out for the starting model M0. It is proposed in the upper formula to neglect intense events on the right side and try to make a linearized inversion. The latter can be expressed via regularized R solution, so-called R solution. And to construct R solution or R pseudo-inverse operator, it sufficient to calculate on the highest singular vector corresponding to the highest singular numbers. To do that, LU decomposition of the matrix is considered for each frequency from a given range. In the experiments, our starting model is good enough and not to need the low time frequency in this case. The choice of target area is because this area is because of the model is complex and it is of great interest for the inversion. So, coming to singular value analysis, so singular spectra, first 768 values for operators acting on model M0 and on model M0 together with diffractors part are presented in this figure. And as one may observe, they are almost indistinguishable. If we take the ratio of these values, we can see that this value is near equal to 1. From this, you can conclude that these operators are almost the same for solving the inverse problem. And in confirmation of this, we present several random comparison of right singular vectors. So this one, and this one. And as one may observe, they are almost indistinguishable. So they are almost the same. And so they almost coincide for these operators. And this explains why, first, why we had such results when we did our first experiments, but it now shows that if we have another model, not good model, but not so good model as in the first example, but this model that we used for standard FWI, we see that we don't have additional information that comes from these diffractions. So this information there is, but in such a way we cannot instruct this information. So then we come to the second option, therefore, and it inspires more confidence in success. So it is based on considering an approximate calculation of the Hessian, its pseudo-inversion, followed by action on the gradient built only on the diffraction component. So in this case, we take only diffraction component and we do projection of this component on the model. So assume that we have the operator for extracting the scattered component of the wave field, then the change formulation of the FWI oriented on the use of scattered component have the following objective function. Then the modified objective functional gradient will take the following form, you see here. And we will concentrate on obtaining the maximum information in one step of the nonlinear least squared method. To do this, we will use Newton method, which states that the choice of the direction of updating the model should be such that the gradient calculated in the updated model is 0. The last brings up to the following expression in the middle, where HM is the Hessian of the objective functional. So the Hessian approximation leads us to the following expression for the updated model here. So now the solution to the inverse problem with the described framework of the modified Newton method was constructed for a group of time frequencies 5, 7, 10, and 14 Hertz. In the first experiment, the effect of only depth point diffractors was investigated, this model. And in the other experiment, point scatterers were added to the entire model, this experiment. So the recovered models are shown here for experiment 1 and experiment 2. As can be seen, even involving only the scattered component in the inversion process carried information about the structure of the medium. When one uses only depth point diffraction, the result has a poor resolution. But if we use larger number of scatterers, this increases the quality of the solution to the inverse problem. So, and finally, I come to the conclusions. The influence of the scattered component on the result of the FWI method has been studied. The results after a standard FWI are almost the same as after diffraction FWI improvement, but we enhance the inversion workflow by incorporating the R pseudo-inverse approximate Hessian operator to the inversion process, and we investigate one step of the nonlinear quasi-Newton method with the enhanced. And we see that with the enhanced workflow, experiments show the possibility of improving with the velocity model via full waveform inversion of diffracted scattered waves. So, and I have to say that the work is supported by RSF grant, and thank you for your attention. And if you have any questions, I will try to answer them.
Can you say it again?
Sorry?
It was muted. Can you say it again? Thank you.
Okay. Thank you. Okay. Are there questions? No. What do you think about the application of your method? Where the benefit of your approach can be
So the goal of this research was to try to understand can we give additional information to the velocity model and to get a better actually macro velocity model for diffraction imaging. And the bad news, I would say, that standard FWI, good news that standard FWI provide us rather good model for this goal. And in this sense, the scattered component doesn't have any additional useful information in this sense. And this is, but we understand that there is additional information, and therefore we try to understand the second what we did. We try to understand how we can extract this information. So when we provide investigation of this way, and we see that information, there is information, and it can be instructed in the sense of model. But as I mentioned, probably for the high frequencies, for the details, it can be useful in this sense, and only in this sense. But the main that for diffraction imaging, update of the model, we don't need additionally apply diffraction of WI for if you want to get the model for diffraction imaging. This was the main goal, and the second, I'm not sure if I answer your question.
Yeah, thank you. Thank you so much again. So the second, you are still the presenter of the second, I guess.
Yes, I'm the presenter in this case. So,
okay. So the title of the paper is Seismic Inversion After Depth Migration.
Okay, so Do you see my screen now?
Yeah.
Yes.
Okay, I will not do full screen. So the title was told, and again, I am the, in this case, I was supposed to be presenter, and I am the presenter, and this is a collaborative work with my colleague, Danil Mitrachkov. So here is the agenda of my talk, and first I will present briefly the introduction, then I will describe model-based seismic inversion and testing result for the implemented algorithm in the time domain. Next, I will come to the seismic inversion result in the depth domain, and I will show examples of low-frequency model reconstruction as a result of seismic inversion, and I will finalize with the conclusions. So, seismic inversion has become a standard procedure which most times is mandatory for predicting reservoir properties. So traditionally, people consider seismic inversion as an algorithm that provides conversion of time or migrated time seismic section into an acoustic impedance section. And however, depth processing is often necessary, and seismic inversion is desirable based on the result of depth processing. The major result of this is one point, and another point, the major result of the standard use of seismic inversion is high frequency component of the model. However, the low frequency component remains in shadows, and although the logic of the inversion operation points out that this part of the model should also be defined. And therefore, within the framework of this work, we investigate seismic inversion in order to determine its capabilities for reconstructing the low frequency component of the depth model. So now let me start to show what is the model-based seismic inversion. So model-based seismic inversion uses a one-dimensional convolutional model, this one, and a low contrast approximation of reflection coefficient, this one. So here S, this is seismic trace, W seismic impulse, R reflection coefficients, and Z acoustic impedance. When we do discretization, the above equations that I showed on the previous slide take the following form. So we have linear equations, linear algebraic equations. And we assume, what we assume that in the upper layer, the acoustic impedance to be known, and we rewrite the system of equation with respect to vector that is logarithm of acoustic impedances, and substituting expression for the reflection coefficient into it. So then multiplying both parts of the system of equation by matrix C transposed, we arrive at a system of linear algebraic equation, and then here the matrices W and D are n by n square and non-singular, and therefore matrix A is symmetric and positive definite. Therefore, we solve the last system by using conjugate gradient method. And to do this, we need an initial approximation and an a priori model of acoustic impedances is used in this case. And hence the name of this type of the inversion, i.e. model-based inversion when it needs some initial model. In the practice, when solving geological problems by seismic inversion, the interpolation of smoothed logging data along the traced horizon provides the initial model. So, in the data, there is, in the observed data, there is a noise usually, and in order to suppress its influence and get an adequate solution, we use a regularization. One of the popular approaches is Tikhonov regularization. It means to move from solving system of algebraic equations to the problem of minimizing the parametric functional. And in order to get smooth solution, we use the regularization method that is called the maximum smoothness regularization. And here alpha is the regularization parameter. So two small values of the regularization parameter lead to the original ill-posed problem, and two large values give solutions that have little in common with the original system. Therefore, the choice of the regularization parameter is important, and one of the most popular approaches for automatic selection that we use this parameter is residual principle. This establishes an explicit relationship between the regularization parameter and the errors in the observed data. So after we realized, we implement this algorithm, we test it, and to test the developed inversion algorithm, we create a model identical to the one presented in this PhD thesis. And then we calculate the ideal seismic trace by convolving the corresponding model deflection coefficient and the seismic wavelet. Here we use 3 pulse with dominant frequency 20 Hertz. And next we apply seismic inversion using data without noise first, but we change the regularization parameter. So alpha 1 and alpha 20 here is shown. The result shows that as the parameter alpha increases, the solution becomes smoother. So everything works as it should work. Then we carry out the next series of calculation for data with the Gaussian noise. The residual principle provides the regularization parameter automatically in this case, and we know that in this specific case, when the noise level is 15%, the result visually does not differ from the result of similar calculation presented again in this PhD thesis. So we decided that in some sense this is the repeatability of the result on the identical, almost identical data that the developed, and we conclude that the developed algorithm works more or less correctly. So then we come to the seismic inversion of depth migration results. So the general scheme is the following. First, we do true amplitude depth migration. For example, this one that is our own homemade migration. Then we provide time depth to time conversion, and after that we can do seismic inversion trace by trace for every spatial coordinate. And after that we can come back if we need to from time to depth back. And I have to note that depth to time conversion, this is not migration procedure, and it works like a rescaling operator. So we just scale from depth to time. It's like rescaling. It's not. It doesn't transform the data significantly. So then, in the next series of experiments, we apply the developed model-based seismic inversion algorithm to the result of depth seismic migration in true amplitude. Since both the migration velocity model and the migration result are specified on a depth scale and seismic inversion works on time scale, as I said, we use the time depth to time transform, and for its implementation, we use migration velocity model that we have from the depth. And thus, through this transformation, we get the original and migration 6B models in a time scale and further convert it into acoustic impedance values. So this is final result I presented. Then we get the seismic image and seismic trace and at a depth scale by using the true amplitude migration, just one trace. And in parallel, we construct ideal seismic image. It means that we provide the ideal result not after the depth migration, but directly from the model. Oh. So, and this is ideal result that we have to get when we do migration without noise and ideally, and when migration works ideally. So, and we see there is some kind of difference. So formally, such ideal trace result of two-dimensional convolution of a reflection coefficient model in depth with the seismic wavelet. So we convert ideal images and depth migration result got in depth domain to the time scale, as I said, and we consider just one trace. One can see that it coincides mostly, but not ideally. There are some discrepancies. So we apply the developed seismic inversion algorithm to both traces. And here on the left, one on the right, one can observe the inversion along the ideal path gives a result that coincides with the true solution with high accuracy. But the result of the inversion of seismic trace after migration is less accurate, as I said, and which is consequence of the difference between the migrated trace and the ideal one, and therefore the result is not of the inversion is not so perfect, but it's rather good still. So this is we result when we did not get optimal regularization parameter. After we get optimal parameter, we've got such kind of result. And so in this case, we apply seismic inversion to the entire studied fragment of the 6B model using maximum smoothness regularization. And the inversion result shows a satisfactory accuracy of restoring the detailed impedance model mostly, except the vicinity of diffraction objects and zones of where we have faults. So in these zones, seismic inversion does not provide appropriate result. And this is was underlined in another study. So next, first, so the inversion results shown here that the seismic inversion shows that the seismic inversion of the depth migration result gives satisfactory result restoring the detailed model of the environment, including a high frequency component. And one can see that this result describes the seismic model, including the low frequency component. And of course, the initial model contains part of the low frequency component, which is used both in migration and inversion, but it is being refined. And to reveal this more clearly, we propose to highlight the low frequency component of the model by smoothing the inversion result. Here we apply the same procedure to the true model in order to see that we do consistent smoothing and we get the consistent result. So, and we use the function with the Gaussian kernel as a smoothing operator. And B here, the parameters that control the smoothness of the resultant function. So next we provide various low frequency component of the true model and the result of the inversion by smoothing with different values of the parameter B. So comparing of the low frequency component of the true model and the result of the inversion of ideal traces and traces after migration shows that the inversion determines these components with a high accuracy. Actually, relative mean square error of the traces inversion result after migration relative to the true model for the components obtained by smoothing using parameter B equal to 0.3 equals to around 1%. When using the parameter B 0.1, the error is about 2%. So, and we see that based on this result, we can conclude that the inversion really determines the low frequency component of the model while restoring it with a fairly high accuracy. So finally, I come to conclusions. We present an algorithm of seismic inversion after depth migration. We show model-based seismic inversion of the depth seismic migration result reconstructs the high frequency component of the model with acceptable quality. It is consistent with the standard application of the seismic inversion to time processing result. And we extract low frequency components from the impedance model and inversion result of ideal seismic traces and seismic traces after migration. And by comparative analysis of the low frequency component of the original model and the result of the inversion, we show that the seismic inversion can recover the smooth component of the model. And such circumstances create prerequisites for using seismic inversion as a tool for refining the depth migration model. So also I have to say that this work is supported by, in this case, RFBR grant, and thank you for the attention. And if you have questions, I will answer them. I will try to answer them. Thank you.
Thank you. Any question?
Sorry?
Any questions?
I think that will be yours.
Yeah, you're right. The noise is terrible. Okay, so thank you so much. In the
Thank you.
meantime, we have the third speaker,
Yes,
maybe?
we have.
Okay. So the next presentation is made by Vadim Lasitsa, I guess. Yeah.
Yes.
The authors are Olga Stoyanovskaya, Vadim Lasitsa, Sergei Anoshin, and Tamara Markelova. The title of the paper is Dispersion Analysis of Smoothed Particle Hydrodynamics to Study Convergence and Numerical Phenomena at Quartz Resolution. Please, Vadim.
Good afternoon, everybody. Thank you for inviting me on and to give this presentation. And the presentation is going to be about the dispersion analysis in application to smooth particle hydrodynamics. The smooth particle hydrodynamics is the mesh-free method which allows us simulating fluid flows and gas dynamics, solving gas dynamics equations and quite a lot of other problems. But as soon as it is based on like particle-based, well, it's a particle-based method. And typically these methods are hard to be analyzed analytically. I mean, there are no such a thing like approximation or something like this if we are talking about particle-based methods. We can approximate like time derivatives, but we can hardly approximate the spatial part of the differential operators. At least we cannot define what approximation is. And in this case, dispersion analysis allows us to understand what is going on and how, for at least we can study the behavior of numerical solution if we try to simulate wave propagation, at least in linear regime, not in all the possible regimes, but for linear wave propagation, we can apply dispersion analysis and see how the numerical solution converges to the true solution. And that's the idea of dispersion analysis, and that's why we tried to apply it to smooth particle hydrodynamics, where we have no solid theorems on the approximation order or something like that. So what is smooth particle hydrodynamics? The idea is that we represent our media, the congregation of particles, which each particle has its own mass, and the smooth function which defines the domain of dependence for each particle. So all the particles which are inside this domain of dependence, they affect this particular particle. All the particles which are not inside this domain, they are they have no direct effect on the particular particle, and that's pretty much the idea. So the in this case, the density can be represented as is given in formula 2, and then one can compute also the values of functions as presented in formula 1, and gradients, and so on and so forth, using gradients of these weight functions W. But and then we can approximate equations of gas dynamics. In this particular research, we considered 1D problem with the equations of gas dynamics, and it's well known that if we consider linear approximation in the vicinity of constant solution, we will get linear acoustic equation with the dispersion relation, which looks like this in formula 4, and it's well-known well-known dispersion relation, stating that the linearized gas dynamics equations possesses two plane wave solutions propagating with the velocity cs in positive and negative direction. It's all well-known things, and now let us try to see what would happen if we try to simulate wave propagation. If we try to apply smooth particle hydrodynamics to gas dynamics equation and simulate propagation of linear wave. In this case, so the equations, semi-discretized equations of the smooth particle hydrodynamics are presented in equation 5, where we see these functions W, which are defines domains of dependence, kernel functions, and also the equation to find to find the velocity equation which define the acceleration and all these things. So to apply dispersion analysis, we need to represent our position of the particle, velocity of the particle, and the pressure, density. We need to linearize them and represent the perturbation at the oscillatory function, and then we can compute the dispersion relation for the numerical method for the SPH, and the dispersion relation will look like this. It's equation 6. So you see that it's quite complex, even though even though the first term here it very similar to finite difference approximation of acoustic wave equation, whereas the second part is quite weird, but still it's here anyway. So in these notations, what we have a very nice thing here is k, which is the number of weight function radii per wavelength. So it's like if we try to make connection between SPH and, for instance, finite differences, this k would mean that the number of stencil lengths per wavelength. It's not a number of grid point per wavelength. It's a number of stencils per wavelength. It's a bit more convenient for SPH. And phi is the number of grid points per stencil. its number of the distances between the particles per stencil. So for finite differences, for instance, if we are talking about, I don't know, second order finite differences, phi would be equal to 0.5. For if we increase the stencil, the phi will decrease, and but we will still have phi equal to 1 over some integer for finite differences. For smooth particle hydrodynamics, it's not the case. It can be arbitrary number less than 1, and this leads us to quite a nice, not very nice conclusions, which I'll show later. Okay, so resolving this the dispersion relation with respect to the velocity, one would get something like this, where and the first thing which we have to take a look at, what would happen if we let phi goes to 0. So if we fix the size of the kernel, but decrease the grid step, and in this case the limit would look like this, and it means where f it's a Fourier transform of the kernel function, and it means that the kernel function should be a very specific function to ensure the convergence at all. And mainly for all the functions which are used nowadays, which are based on the high order spline approximations, they satisfy this relation, and moreover they goes to 1 for large for small h kh. Okay, that was the first conclusion from the analysis, and the simplest one. So if we have infinitely small grid step, the method supposed to converge. It's great. At least it's just classical asymptotical analysis. At least for extremely small grid steps, everything is gonna be okay. But of course, it's not the most interesting case, because we need to be able dealing with the method using quite coarse meshes, and we need to see what would happen if we use the coarse mesh. And here is the error if we use error of the SPH method, if we use different splines for the kernel functions, and the horizontal axis, I don't know why it's negative, but it's supposed to be positive, and horizontal axis represent the parameter inverted parameter phi. So the number of grid points per, no, it's not the number of grid points. Yeah, yeah, it's supposed to be a number of grid points per the stencil, but inverted. And you see that if we have these numbers not close to the 1 over integer, the error may be irreducible. I mean, whatever we do, the error goes to some value. So okay, a bit different point of view on this on the thing is that, again, it's still about the irreducible error. If we consider the two plots of the velocity, like of the numerical solution, and the vertical axis is again the number of grid points per stencil, and the horizontal axis represent on the left, it's a number of grid points per wavelength, and the right plot, it's a number of stencils per wavelength. And if we consider it in a like convenient way, where we deal with the number of grid points per wavelength, then we see that for some values we will have completely reducible error, whatever we are doing with the, even we try to increase the number of grid points per wavelength, for some ratios of grid point per stencil, we will never have convergence at all. But for and then there are some values where we still have irreducible error. This dark guy will never go lighter and lighter, so it's gonna stabilize over here and never produce accurate solution if we choose the number of grid points per stencil in proper way. And that's a cross plot of the same
Go to the conclusions, please, because.
Okay.
Can you
Yeah. So the main conclusion here is that yeah, that's how the solution would look like. The main conclusion is that smooth particle hydrodynamics in general will not ensure you the convergence of the solution. But to be able to solve the problem, you need to choose the grids, the stencil very carefully. So if you choose the number of grid points per stencil in proper way, you will never get the solution, the correct solution using SPH. So you need to be very careful about it. Otherwise, you will have to reduce the grid step significantly to get even like more or less proper solution, not even accurate enough, but maybe proper. That's pretty much it. Thank you for your attention.
Thank you. Time is over, so no time for questions. The last presentation is from Backlab Scala.
It's going to be one follower on the internet.
Sorry?
There is only one listener.
Oh, okay.
No, we can make it.
There are
A bit more.
Yeah.
which one is your presentation?
The title of the paper is Critical Points,
This one.
Properties of Ordinary Differential Equations as a Projection of Implicit Functions using Spatiotemporal Taylor Expansion.
No, it's not mine.
It's not, okay, so sorry, it's yours.
Yeah, might be.
Okay, but just a second.
Okay.
I need to share the screen. Okay. Now this
Probably
page.
you have to click here, and I take the.
Okay, you can also come here.
I see. I am okay. I am usually used to stay and walk.
Yeah. I understand. So,
It's short. Okay. Does it work? Okay, my name is Václav Skala, and I'm from the University of West Bohemia in Pilsen and Czech Republic, and also at the Department of Military Robotics, Faculty of Military Technology, and University of Defense, Brno. So, something is wrong. It's not the way how I would. Yeah. Okay. So, a couple of pictures from Pilsen. So, Pilsen is a very old city. We have a St. Bartholomew Church. It is the highest tower in the Czech Republic. The second picture is about our building, newly built about 10 years ago. And we have also the second largest synagogue in the Europe. So nice place to visit. And of course, because Pilsen is very famous because of beer. Beer was actually the bottom fermentation of beer was invented in Pilsen. So that's why all the good beers are called Pilsners. So you have to come and taste if you have a chance to visit our place. There is a problem because it's showing only part of that. Alt L or something like that. Yeah. Thank you. Thank you very much. And I hope that at the end of this talk, you will not be like this guy that is taken from the mysterious castle in the Carpathians, very famous film. Okay. So why I'm actually presenting that? The physical problems are usually solved using the partial differential equations and or ordinary differential equations. And if you have the ordinary differential equations, especially in the field of visualization, there is always a problem to find the critical points. Critical points are actually defined as a point where the derivative is equal zero. So it's very difficult, and actually we came across with this problem when we were solving some measured data of the tornado big files, and it was really difficult. Okay, so the problem is that we have actually two different equations. One is the ordinary, that means x dash is some function of xt, and the partial differential equations, I'm not going to this part, is something different because we are having it's a different formulation. I will go into it more detail. I will use the small letter as a value. Bold vector is bold symbol is a vector. Big vector bold is matrix, and xi will be used for the time spatial temporal data. That means that we will have a spatial coordinate x and t as a time let me say axis or use. The problem is that if we are using the RBF for solving the differential equations or partial differential equations, in many cases you can see that the distance between 2 points is given as a Euclidean norm, and they are mixing together the spatial coordinates with time coordinate, and it is invalid because you are putting together different units. That means you are mixing meters with seconds. So the ordinary differential equations actually have two forms. One is the what is on the second line, but we will look to the implicit formulation that is more general. I put here derivations according to x and t using the some notification that is described detailed in proceedings, and we will use actually the Taylor expansion for the spatial temporal case of the function f. So that are some not usual let me say formulations that has to be used, because if we are differentiate according to t, according to time axis, we have to be a little bit more careful, because somewhere here is the expression a little bit more complicated. So at the end we are getting the Taylor series for, or Taylor expansion for the function f for spatio-temporal argument that is described in the formula here. And we have to look that the eta is actually again the spatio-temporal argument. So at the end, we will finish with this formula, and the ax squared should be read as a quadratic form or quadratic form of x transpose a t. So the formula is quite complex. I hope that I haven't made any mistake. So when we are going to the singular point, so we know that the f psi is equal to 0, and derivative should be also equal to the first derivative is also equal to 0. Actually, the singular points are very important because it enables you to classify the vector fields of flow, for example, if there is a rotation, if it is a repeating point, and so on. So being very, let me say, not going into details, we can see that actually what we have to put this this equation equal to 0, and that actually defines the critical point. And the critical point is defined as x dash equals 0. That means for all x1, x2, xn is equal to 0, all the elements. So that is actually this expression. Using some mathematical, let me say, operations, we came to the equation 14. And because we are now making the restrictions of T invariant system, because for the T variant system is more expensive, more difficult. So the position of the x is constant in time. So at the end, we are getting this nice formula that is actually saying that the first derivative of the implicit function f according to x partial differential equations multiplied by the acceleration actually of the point x is equal to 0. This is actually a significant result because it's enabled us to detect more reliably the critical points in the vector field visualization. And also there is some connection with the some other known physical behavior. I put here just for the imagination, how does it look like for very simple examples, synthetic examples that were used for testing. So we have two equations here, two critical points are here, three critical points are here. And if you have a measured data, of course, it is not so nice because you have to somehow represent those vector fields. For that, we were using the radial basis functions, interpolation and approximation. That actually is very convenient because it leads to a solution of linear equations. The linear equation, the system of linear equation is really large. In our case, it was something like 1 million by 1 million and more. So there is another synthetic example showing what is actually causing the critical point, because critical point is here, and according to the different changes of C value, it's the results are different. Okay. That is just the proof taken from the proceedings to show you that it is valid. So the conclusion. I try to briefly describe the new conditions for critical points of ordinary differential equations using the Taylor expansion for time for spatio-temporal data. Conditions increases, actually the developed conditions increase robustness of detection of critical points, especially if the data are acquired from some sensors, and general form is derived. So I think that it is all. I would like to thank to colleagues at the Shandong University, Jinan in China and West Bohemia for stimulating this work. So we have time for questions. I hope that I will be able, and if you would be, No? Sorry, references are not included. They are included in the proceedings. Apologies for that. Thank you very much.
Thank you very much, Václav.
I try to keep the time.
Yeah, to stay in time for the keynote. Thank you so much. Okay, very nice and good presentation. Thank you. Any question from the
Audience?
Audience, yeah, from internet. I mean. Okay, if not, we can close the session.
You are welcome to visit the proceedings.
Okay. Yeah, they will be available in the next days. So there is a small delay, but okay. Thank you so much. We can close the session.